Hello, we're almost there, friends. We've reached Module 14, our last module. We're going to be talking about solving exponential equations in this module, and then later on we'll solve some application problems using exponential functions and logarithmic functions. So, when we're dealing with an exponential equation, we have two methods that we can use to solve. One thing that would always work is going to be converting, and we're no stranger to this conversion formula. We can change exponential to logarithmic and logarithmic back to exponential. But we also have an option to try and get one base equal to one base. And if we've got the same bases, then we can drop the bases and let the exponents be equal. And then we also have another strategy, a third strategy, which I personally don't use as much, but we can take the natural logarithm or common logarithm of each side of the equation and then use the power property to bring that exponent into the front as a factor. So, example 1. Move it right there. We have an exponential equation. So the main things we try to think about bases. So when we're thinking about bases, we're thinking about powers. Logarithms are ways of counting by powers. So if you think about, say, base 2, we've got some powers, base 2. 2 to the 0 is 1. 2 to the first is 2. 2 squared, we get 4. Cube it, 8. To the fourth power, 16. The list goes on. And you want to be familiar with some of these common numbers, like base 3. We would get 3 to the 0th is 1. 3 to the first is 3. 3 squared is 9. 3 cubed, 27. 3 to the fourth, 81. Again, the list keeps going. So we're thinking about numbers and raising them to powers. So when I see 4 as my base on the left side here, I want to think about taking that 64 and writing it as a power of 4. And we can't always do that, but if we can, it can really shorten the amount of work for a problem. The good news is I know that 4 cubed is 64. So if I rewrite the right side, that value 64, as 4 cubed, now I have one base equal to one base. I can drop the bases and say that negative x equals 3, or rather x equals negative 3. And you should always check, the numbers should always plug into the original problem and make sense. But we don't end up with extraneous solutions in this situation so much because the domain of exponential functions is all real numbers. So there's no domain restriction that comes in place when we start the problem. Okay, example 2. 2 to the 3x minus 1 power minus 4 equals 28. So in this situation, I'm going to rearrange a little. I'm going to add the 4 to both sides of the equation. So I've got 2 to the 3x minus 1. If I add 4 to 28, that gives me 32. So if I look on the left, I have base 2. I have a base 2 raised to a exponential variable power. Can I write 32 as 2 to a power? And because I'm familiar with raising 2 to powers, I know that 2 to the 5th equals 32. So on the right side of my equation, instead of writing 32, I'm going to write 2 to the 5th. And now we have one base equal to one base. The bases are the same, so we drop the bases, and I end up with 3x minus 1 equals 5. Add the 1. 3x equals 6. Divide by 3. X equals 2. So example 3 and 4 here become a little more complex, so we just want to make sure we know what we're paying attention to. Example 3, I have 3 raised to a quadratic power, x squared plus 4x is in the power, equal to 1 over 27. So on the left, when I see that 3, I'm thinking, okay, base 3. What are some powers of 3? Is 27 a power of 3? And 27, this is the same as writing 1 over 27 is 3 cubed. So because it's in the denominator, that could also be 3 to the negative 3. So rewriting this, I can say 3x squared plus 4x equals 1 over 27 is actually equal to 3 to the negative 3. So you'll notice now we have one base equal to one base. We'll drop the bases, set the exponents equal, and now we have a quadratic equation that we need to solve. So quadratic equations, we always put them in descending order, equal to 0. I end up with x squared plus 4x plus 3 equals 0. This factors x plus 3, x plus 1 equals 0. And I end up with x equals negative 3 or negative 1. And we get two solutions to this problem. All right, example 4. 6 with a quadratic power, that's x squared minus 7x plus 16 equals 36 to a linear power. The power is 6 minus x. So we're solving an exponential equation, and we know it's exponential because the variable is in the exponent. So if I look at the left side, my base is 6. I ask myself, can I write the base on the right side as 6 to a power? And we know that 6 squared equals 36. So I'm going to rewrite my equation. I have 6 to the x squared minus 7x plus 16 equals 6 squared to the 6 minus x. So now this is where we want to make sure we're really careful when we simplify. We can't just drop the bases yet because we have a power to a power over here on the right side. And a power to a power you need to multiply. So there's some distribution in here. And I've got 6 to the x squared minus 7x plus 16 equals 6. This exponent on the right turns into 12 minus 2x. So now I have one base equal to one base. Can drop the bases and set the exponents equal. X squared minus 7x plus 16 equals 12 minus 2x. So we're solving a quadratic equation still. When things are quadratic, we know that because they are x squared, and we want them to be in descending order in relation to 0, so we can try to factor. X squared, I will add the 2x, gives me minus 5x, subtract the 12, I get plus 4. And so as I said before, most of these are going to factor, so it should be pretty easy for you at this point. Although we know, realistically, equations don't always factor, and sometimes we have to use our quadratic formula. But again, most of what you should see here will factor, and this does. We have x minus 4, x minus 1 equal to 0, and that leaves me with x equals positive 4 or positive 1. We have two solutions which both check in the original equation. So we have a few more examples to solve in this section of our notes. All of the examples we previously did in this section, the previous 4, they all had similar bases on either side. But that doesn't always happen. So we're going to look at what to do and how to solve a problem when we cannot create some base relationship and say, well, 36 is 6 squared. I'm going to simplify it like that. I have base 10 on the left, and I do not know 10 to a power to equal 4. And I can write 4 on the right as 2 squared, but that's not going to help me to get anywhere near 10 because I can't write 10 as a power of 2. So what we can do when we're solving these equations would be to take the log or the natural log of both sides. And either the common log base 10 or the natural log base e will work. You'll get the exact same answer either way. The main thing is that you can make a choice to use one that might be a little simpler. So if you remember, common log is base 10. Looking at this problem, I have a 10. So I'm going to use common log, take the common log of both sides. That's the log of 10 to the 6 minus x equals the log of 4. So I take the log on both sides of the equation. Once I've done this, it's very easy for me to see that log base 10 of 10 is going to cancel. And we did a property in the last module, 13, that let us know that when I have log base 10 of 10 to a power, we can just cancel the log and write the power. So I've got 6 minus x equals the log of 4. And we're just trying to solve for x. So I'm going to subtract the 6 over. Negative x equals log base 4 minus 6. And divide by a negative 1. X equals 6 minus the log of 4. So that is my exact answer. Of course, we can write it as an approximate answer and say that x is approximately 5.398. And if I were to try and type that into my calculator, I'd say 6 minus, I would use my log button, and then we would have 4. Okay, so because it's a common log base 10, I can type that directly into my calculator. Example 6, we'll do the same thing. And we have a choice to make common log or natural log. And when I look at example 6, which reads 5 equals 3 to the 12x power, I don't see an e or a 10. So I'm going to take the natural log of both sides. The natural log of 5 equals the natural log of 3 to the 12x. So at this point, nothing really simplified out, but we can use our power rule. So this is the natural log of 5 equals 12x times the natural log of 3. And by commutativity, if I wanted to, which I don't need to, I could rearrange that multiplication and say x times 12 times the natural log of 3. So isolating x, we just have to divide by this coefficient. And doing that gives me the natural log of 5 over 12 natural log of 3 equals x. That's my exact answer. And my approximate answer I would get by typing that straight into the calculator, 0.122. So exact versus approximate. All right, our last two examples. Example 7, 3 to the 5x equals 17 to the x minus 8. 3 to the 5x equals 17 to the x minus 8. I'm going to take the natural log of both sides, 3 to the 5x, and the natural log of 17 to the x minus 8. So at this point, I use my power rule on both sides, and that's going to let me get those exponents down in front of the problem. So I have 5x ln 3 equals x minus 8 ln 17. And so on the left, I didn't need parentheses, but on the right, I need to make sure I use parentheses because ln 17 is a number, and ultimately I'm going to end up distributing that 17 to both values there. So I've got my parentheses. I'll distribute. I have x times 5 ln 3 equals x ln 17 minus 8 ln 17. So I have two terms with an x. I'm going to get both of those terms on the same side of the equation. X times 5 ln 3 minus x ln 17 equals negative 8 ln 17. Because both terms on the left have an x, we can factor out a GCF, and then we'll be able to divide. So if I factor out an x, that leaves me with 5 ln 3 minus ln 17 equals negative 8 ln 17. The last thing I'll do is divide. I end up with x equals negative 8 ln 17 divided by 5 ln 3 minus the natural log of 17. And this is my exact answer. And if we were to type that into our calculator, we would end up with approximately negative 8.521. All right, we have one last problem here to solve. Example 8. I'm having a hard time drawing this line. There we go. So example 8 is an exponential equation. We need to do some rearranging first. So the first thing I'm going to do is subtract 3 from both sides. I have 4e to the 2x plus 1 plus 3 equals 23. And I'm going to subtract that 3 over here. So 4e to the 2x plus 1 is 20. I'll divide by 4 on both sides. E to the 2x plus 1 equals 5. So just that little bit of rearranging, moving terms over. Now it's pretty basic. I can take the natural log of both sides of the equation, the natural log of e to the 2x plus 1 equals the natural log of 5. Since the natural log and e, our base, are both in terms of e, I can cancel them, and I have 2x plus 1 equals the natural log of 5. And in 2 steps, I'll subtract 1 and then divide by 2. 2x equals the ln of 5 minus 1, and that's all of natural log 5, then take away 1. And then divide by 2, x equals the natural log of 5 minus 1 over 2. All of that is over 2. And if we were to write this approximately, we would end up with 0.305.